Okay, this is section 15.8, electric flux and Gauss's law. This is the last section of the chapter, and Gauss's law is really helps us simplify uh, determining the electric field inside a particular volume. First, let's talk about flux. Uh, you can now. I know when we were talking about individual charges, positive, negative charges, the uh, electric field lines would be emanating kind of in a circular direction. Well, you can think of this as a charge or maybe a series of charges far away, and in the far field, these electric field lines are all parallel. That's the situation we have here. And we want to know the number of flux lines, electric flux lines that go through this area A. And we do that, the number divided by the area is approximately is proportional to E. So N is equal to the number is proportional to the electric field times the area. And so we call this the electric flux, and it's the capital phi, capital phi sub E is the electric field times the area. In SI units, it's Newton meter squared per Coulomb. Um, Now, when you're uh, going through at a particular angle, the normal to this, we need to consider the normal to the surface, and the normal to the surface makes an angle theta with the electric field, and the A prime here is the projection of the area A onto this perpendicular piece, and it's A cosine theta. So the electric flux is equal to EA cosine theta. Um, the number of field lines that go through the area A prime is the same as the number that go through area A. And you can see that if they pass through this perpendicular piece, it goes through this slanted piece also. Okay, now we can define a Gaussian surface, and that Gaussian surface can be made any shape you need to make it for the problem at hand. And with this Gaussian surface, we know that the electric field is equal to KE, the same KE that we used in the Coulomb force, times Q divided by R squared. Oh, well, that is the original definition. Now the flux, the electric flux, is E times A, so that's the KE Q R squared, and the area here is the surface area is 4 pi R squared. So the E is equal to 4 pi KE Q. Now, so KE is equal to 1 over 4 pi epsilon 0, where epsilon 0 is the permittivity of free space, and it's equal to 8.85 times 10 to the minus 12 Coulomb squared per Newton per meter squared, or Newton meter squared, but that's all in the denominator. The Newton meter squared is all in the denominator. Okay, now you can see that this is all. Well, let's go back. Let's go back and look that the KE, if KE is equal to if 4 pi KE is equal to epsilon 0, then 4 pi KE is equal to 1 over epsilon 0. And so the electric flux is equal to 4 pi KE Q is equal to Q over epsilon 0. Now, this is a great achievement. It tells us that the electric flux through any Gaussian surface, and we can make that surface anything that we need, the electric flux is equal to the Q inside the surface divided by epsilon 0. And that's what what it comes down to. The Q, the electric flux, is equal to Q inside divided by epsilon zero. Now here is a um, we're going to study this in upcoming chapter. The it's basically a parallel plate capacitor where you have the charge, you have the positive charge on one side and negative charge on the other, and the sigma is the linear charge distribution. So that's the charge inside divided by the epsilon zero. E is equal to the sigma divided by the sigma divided by epsilon zero. And outside the plates, they cancel. So it's the outside the plate, the electric fields cancel. And that's it for this. I'll post the topic summary also. And so that does it for chapter 8. I mean, I'm sorry, for section 8 of chapter 15.